Okay, I'll do that. Yeah. All right, let me continue my lectures first.
Sir,
Yep.
what chapter is this?
What chapter is this? Okay, input output.
Input output.
Yeah,
Okay.
if you look at Sagi, I mean, a blackboard, yeah, input output. Today we're going to cover input and output, yeah. For those who just came in, we are starting with input and output for today. Okay, so I'm going to continue with slide number 2. Yeah, I'm still with the very first slide. Yeah? Okay, so let me continue where we stop. Without I/O, without input output, as we all understand, there is no possibility for the input data to be managed, yeah, into the system, as well as to generate output from the system. I think we all understand this. This is very basic. So that's the reason why we need to understand how the I/O works uh, together with CPU, together with memory, so that we understand the operation in as a overall. Basic model of IT computer system, as you all have covered in any IT subject or basic subject, where it looks like this: input, and then the input will be processed, and then in order to generate output, right? Or it will be as simple as the diagram that you see at the top, where you'll have an input, process, and then output, and then the process need to be either shared or need to be displayed for temporary, or need to be safe permanently. Yeah, if need to be safe permanently, that's where storage comes in. Otherwise, storage doesn't play a role here. Only input, process, and output. I think those are the basic stuff. Uh, Moving forward into slightly more detail, there are over 20 to 30 I/O devices that normally, or I will say usually, we don't notice it. We don't notice. Normally, in a face-to-face class, what I will tell the student is, for each one of you to identify 2 or 3 I/O devices. The common I/O devices that we know normally is keyboard, mouse, touchpad, touch screen, scanner. But if we look into detail, if we look into slightly into, yeah, more detail, what are the I/O devices available in the market or within, surrounding us? The list can be actually very long. And we got to be careful sometimes. Don't get confused or don't misunderstand with storage. With storage, for example, we need to make it very clear, like USB, whether it is really a I/O device, or it is a combination of I/O and storage. So we will discuss that. Yeah. Okay. As far as input and output devices are concerned, keyboard definitely, yes, one of the input output devices. But as you know, keyboard itself doesn't store any value or any data. It simply accept the value, and the rate of data transfer is very low. Control is definitely external, outside the CPU. Anything outside the CPU we call external, as you can see the diagram here. Anything outside this process is we call external. Anything inside the process or this box we call internal. In other words, I can also say anything outside CPU is called external. Inside the CPU we call internal. That's the normal term that we use. And keyboard handles what type of characters, what type of data? Character based. Character based. We did discuss about this previously. How many characters are there on the keyboard, and how keyboard translate each character into the system and vice versa in the ASCII format. Just for those who forget about it or not very sure, keyboard manage all the input and output based on ASCII, ASCII table or ASCII characters. Then we have mouse, touchpad, it's considered input. The data rate is still very low. Control external, also characters, or we call signal based, isn't it? Because mouse is based on either you click or you don't click. When you click, there is a signal. When there is a signal, that means there is a single character or a character is being passed into the system or from the system. Scanner the same, because scanner, remember when we did IT, we do call OCR, OMR, optical character recognition or optical mark recognition. All those are characters. So still a scanner is an input device. Data rate is of course medium, much faster than keyboard and mouse. So it is external. And scanner read data in a block as an image, So that's why they call it block, not character by character, unless the old version of scanner where you read character by character, or it was known as a OCR, optical character recognition kind of scanner. But the scanner that we have today is very high end, very high end. You read the entire image as one image and transfer as one block. Then we do have voice as also input devices. For example, when you do voice recording using your phone or any devices, it also being transmitted in a block, one block at a time. One block at a time. That's why you do recording, then you stop. You do recording, then you stop. It's considered one block of data. It cannot be too huge. Is basically no one saying that it cannot be too huge, just to make sure the bandwidth is reasonable. So we control, we don't want too large. But of course, there is some limitation. Then we do have other devices which handles input and output, such as sound recorder or speaker or recorder, basically, recorder, we call it recorder. If you look at USB, we cannot consider USB as an input device, because USB, no doubt, it takes in value, but it is also store value. So if you are referring to the USB port itself, then it can be considered as an input port. But if you are referring to the USB storage, then it is a storage. But here in this line, in this particular line, they are referring to the port, USB input and output port. Then they also referring here to the network port. What you call the network port? I hope all of you still remember, or we will cover this under network. Or you should have covered this under data communication and network in your diploma program. We call this RJ45 or network port, network port. That is also I/O, input output. Of course, network port can go into high to very high speed. It goes into gigabit and so on. From megabit, gigabit, and so on. Then we do have a printer, also I/O devices. We are talking about all I/O devices here, just to refresh yourself. The list can be very long. Graphic display, This includes your display, all your CRT. Those days we call CRT. Now we call it flat screen or smart screen. Any kind of display, tablet display, phone display, and when we call display, it is actually output. Yeah, output is, or in other word, we just call it screen, isn't it? Display screen or screen display. Then we have flash drive, which is a storage, magnetic disk, very old type of storage, solid state drive. Yeah. Then we have optical drive, not very popular nowadays, but we used to popular at one point of time. Then magnetic tape, very old storage as well. Okay, why they give you the list? Simply to refresh yourself that the list can be even longer than this, but this is how input output devices are being used within the computer system. And each IO devices has its own rate, what we call data rate, data transfer rate. The basic measurement is BPS, bits per second, bits, BIT. Anything lower than 5K BPS is considered low. Medium is less than 10 meg. If you still remember coax cable connections, maximum it goes up to 10 meg. Those who are familiar with networking, anything higher than 10 meg, right up to 100 meg, for example, your RJ45 Cat5 cable, for example, can go up to 100 meg, is considered high. Anything higher than that, for example, gigabit speed can go up to 1000, yeah, or 5 megabits per second. We call very high. And even higher than that, for example, if we use fiber and so on, yeah, it's considered very high speed. So I just want to refresh you on the data rate, but that is not our main focus here. Our main focus here is IO, input output. So the whole idea is your computer system, don't just focus our discussion into PC. Let's open up a bit. It can be any devices, because we got to go away from the way we used to think in a very conventional method into very open, because today we have all kind of devices. We have vacuum cleaner running around our house. We have a drone, yeah, uh, being operational, and these drones are taking in input and output from quite a distance in a different form. Everything wireless. We have a remote control car taking in input and output continuously in a different format. So when you look into this kind of devices, that's the reason why I just mentioned to you, don't restrict our understanding or our discussion only to PC. Today, we got to open up our thinking. We got to consider devices or Internet of Things. So when we consider Internet of Things or devices, our discussion go beyond computers, beyond the system, beyond the PC, beyond the tablet. So it can be any devices, yeah, any devices. So the discussion here, it can be any devices, any IoT, Internet of Things. So all these devices or Internet of Things, or sometimes we do call peripheral devices, requires IO, and it has its own very specific or multiple IOs. And one of the common IO today that we all know is the USB drive, USB. Either it is the normal drive or the mini USB, which is becoming very common. And of course, Apple, they have their own uh, ports and so on, very customized. But let's talk about the common one, USB. Uh, so this USB has its own uh, data rate. Some USB handles or manage very high speed, some low speed. And also the same goes to internet port, yeah, internet port, which is connected to your devices. Like what we mentioned earlier, some are connected at a very low speed. I don't know how many of you still remember coax cable works the maximum 10 meg. That's it. Yeah, 10 meg. That's the speed. But if you are talking about uh, RJ45 or coax, Cat5 cable or Cat6 or Cat5e, which operates at a higher speed, up to 100 or even more, then the I/O connected to those network cables need to operate at a higher speed. Yeah, so that's the whole idea. So what I'm trying to explain here is, don't limit our understanding or our discussion just to very simple I/O devices such as keyboard, mouse, and maybe one or two old ports. Let's open up our discussion into the ports, the new ports that we have today, including HDMI, for example, yeah, where the transfer rate is quite high and handles more or huge volume of data. Especially the data that we are talking today is about, yeah, video streams, broadcasting, uploading, and downloading. So we got to open up our discussion into that mode, rather than just character by character. It's not just keyboard and mouse anymore, but we have to consider about streaming of data, uploading and downloading of data. So that's what is happening today. Yeah? The internet world is all about. So I/O, as we understand, is directly connected to the CPU, yeah, with some interfaces that we understand. There is a bus in between. There will be a interface in between the I/O and this component, but directly or indirectly, they all connected as one big unit. Only when all these components, I/O, CPU, memory, when they are connected, we consider that as one system. Yeah, one system. So simple I/O configuration. I think all of you understand this. I don't have to go into very detail. Everything is connected, and there is one additional more specific component that we're going to talk next is what we call controller. Simple I/O controller. It's the same like what we have in the CPU. In the CPU, we were talking about the control unit. Remember the man in the LMC, the man in the LMC with the clock, with the counter, with the counter or with the clock, which behave as the controller. So the same thing is happening here. In a system, we have a controller. Uh, when it comes to I/O, we call I/O controller. When it comes to CPU, we call controller, control unit. When come to memory, we will call with very specific name related to the memory. When come to interfaces, we will call very specific name, yeah, related to the interfaces. Right now, it is related to I/O devices, so we call I/O controller. So what is the function of this I/O controller? Definitely to manage and to control the data transfer. Yeah, data transfer, because what you are transferring through the I/O is data, right? I'm very sure you will agree with that. So what we are transferring is data. So to control the, the data, either character by character or bit by bit or block by block, all managed by the controller. So there is a slightly more complex I/O module in your in the current slide, like what I showed you, what I'm showing you. Let me explain briefly. Again, I would like to highlight this. Definitely in the exam, they're not going to test this much of detail, but it's good to understand how the whole system works. So you have the I/O devices over here. Yeah, I/O devices such as it can be keyboard or mouse, a display unit, because it can be input or output. Remember, it can be printer or it can be scanner. So data is moving in and out. It can be going in or coming out. There is no particular error here or arrow, so it can be in or out. So all this data will be managed by the I/O controllers. Yeah, all this data will be managed by these I/O controllers. And then this I/O controllers has its own very specific function, which we're going to discuss in the next couple of slides, either to manage data or to manage address or to manage something else. Yeah. And in order to transfer data or address or anything else, when I say anything else, it can be just a signal. It all depends on, yeah, depends on the type of data that you are taking in. Because the data comes in, it could be a character, it could be in a raw data, it could be a text, it could be a sound, it could be a audio, it could be a video, we don't know. Or it could be just a click from the mouse. If it is a click from the mouse, it could be just a signal, one bit, yeah, then it is just a signal. So if it is a signal, for example, you need to trigger a point in another component, for example, then you just need the address of that signal instead of the data. So that's the reason why I say this I/O controller is a very specific device which will manage the incoming data or signal in accordingly, yeah, to be sent or to alert the I/O component or the devices itself, yeah, which is like the CPU on your right hand side, the CPU or the ALU or the memory, which we don't see here in this diagram, but possible a memory or maybe a virtual memory or maybe a RAM, we don't know. But this is how your data will be moving in and out between I/O devices and the CPU, because our discussion over here is all about I/O and CPU. Yeah, the discussion continuation from last week is I/O to CPU. That's why you don't see a memory here. But definitely I'll bring in memory into our next discussion, because memory also, when I say memory, it's the main memory, yeah, RAM. And also we can extend our discussion with or into the storage. So we need to look into all this as one big system. And you need to understand in detail how data is being transferred from I/O devices, either one way or two ways, using all the what we call I/O controllers. Okay, let's move into slightly more detail, slightly more technical. Like what I mentioned earlier, these sessions will be slightly into more theoretical and slightly into more technical. Reason is about how overall computer system operates. Yeah. In other words, how the I/O communicate with CPU, communicate with memory, communicate with storage, as well as how data and signals are being moved or being passed within the system. Why we are doing all this? Remember, our earlier discussion was based on the LMC, yeah, little man computers. So we are trying to understand how the LMC can be applied and how the LMC uh, can be compared with the IT system, yeah, with the computer system. So in order to continue our discussion, we will look into some of the program I/O, yeah, especially related to CPU, and then also we have interrupt driven I/O, as well as some related to memory. Remember, I told you earlier, when it comes to different component, there are different controllers. So CPU, we have control unit, and then for the input and output, we have interrupt driven IO, and for the memory, we have what we call direct memory access controllers. So we need controllers everywhere. Otherwise, all these components cannot work as one big unit, but they work as a very special or very specialized unit, very specific unit. It has its own function in the system. It has its own tasks. So that's the reason why every single unit need to be managed on its own. It's not like human being. Human being, we just have one brain, and our brain controls everything, coordinate everything accordingly in a very smart way, yeah, in a very smart way. That's why uh, the computer system cannot be as smart as us as of today. The computer system still lacks many things, but definitely the technology is moving there, is getting there. As you can see, some of the robots today are doing wonders. But when come to the detail, everything is being controlled by the controllers. Controllers. That's why it's very important to understand the controllers. So with that, let me move on our discussion on I/O controller, which comes under the program I/O. Stop me, yeah, stop me. Otherwise, I might go a little bit fast, or you might get bored because I'm not communicating with you frequently, and the number of students that I have here is quite large. There are almost 60 students here. So please stop me if you need further clarification or understanding. And what I might do is I might switch and ask questions, so that you guys are with me. You guys are following me, right? Okay, let me continue with that. I/O data and address registers in CPU. So registers in CPU is very important. Remember, when we talk about programming in assembly language or programming in low level languages, today more and more people are talking about AI and machine learning, which is very high level languages, very smart and complicated, sophisticated. But all those languages are based on very low level languages, where we started with assembly language and then we move on to the different generation as what we have today. So when come to assembly language, we need to consider registers in our programming. And I did mention before the break, there are 32 registers in the CPU. And out of the 32 CPU registers, systems are using 16, and it allows us to use 16. So normally we will label it from, for example, R16, R17, R18, and so on, right up to R32. R1 to R15 will be used by the system, yeah, or R0 to R15 will be used by the system. Other basic stuff that you need to know is, for example, what it means or what is the size of the one word, yeah, the size of the instruction in your system. Remember, we talk about, or I did ask you some basic questions. What is the difference between 32 bits architecture and 64 bits architecture uh, last week or before the break? I hope some of you have found or managed to get the answers or clarification. Otherwise, please continue to search and make sure you understand what is the difference between 32 bits architecture and 64 bits architecture, for example. And moving to the servers, 128 bits architecture and so on. And what it translates into what we call one word. Yeah. So I would like to explain what it means by one word transfer per IO instruction here. Meaning, when you need to pick up one instruction, one command from memory, for example. Because remember, we fetch our instruction from memory in order to execute in the CPU. So when you fetch an instruction from the word or from the memory, we call that one word, one word. And the size of what we call one word varies today. Those days, one word was 8 bits. Then when the architecture changed to 16 bit, we call 16 bits as one word. Then later the architecture changed to 32 bits, we call 32 bits as one word or double word. So things changes according to the architecture. So if you have 64 bits architecture machine today, there is a possibility that you can even call the 64 bit as one word or four words or two words. It depends on the architecture. So what the CPU understand is when you pick up one instruction from the from the memory and you load it into the instruction, it is considered as a one word, one word transfer per IO instruction. Guys, I can talk about all these topics for hours. Uh, the other term that I would like to touch here is I hope all of you also understand what it means by MIPS. MIPS, million instruction per second. That term is very important as well. Even though you don't see here in the slide, but sometimes it's good to understand and use this kind of terms when you answer your questions. So let me go back to the screen to my meeting. Who understand what is MIPS? You type here, type in the chat, MIPS. What it means by MIPS? Or I can type for you. Just share with me what you understand by MIPS. Anyone? Type what you understand by MIPS. Million instruction per second. Okay, right? Brian, you're right. So what do you understand by million instruction per second? That's my question actually. What it means? For example, if I tell you 8 gig of RAM, you understand the size of the RAM is 8 gig, right? That is the measurement or that is the understanding. 8 gig of RAM means we understand the size of the RAM is 8 gig. The size of the storage is 8 gig. What you understand by million instruction per second? MIPS. And which component or which unit in the system where we can refer or uses this measurement or uses this MIPS?
Is it RAM?
Okay, someone answered RAM, and I see a message here. It means measures computer central processing unit performance. Okay, you are correct. You're correct. It measures, yes, it measures the performance of the CPU. Okay, when you guys buy laptop or desktop today, or even tablets or any devices, you see the speed, isn't it? Gigabits or in hertz, HERTZ. What it means? It means the speed of the CPU. The higher the number, the better. Especially for those game lovers, where you play games, you want your processor to be a faster high-end, super fast processor, and definitely you have to pay more for it. So what are you paying is actually to have a better number, to process more millions instruction per second, higher number of instruction per second. The basic computers, yes, it can be considered as a benchmark. The higher the number, the better the performance, right? And this is the job of Intel today. Intel and AMD and Hitachi, for example, they all fight to each others to produce higher MIPS. Even the older computers, very old generation of computers, 486, 386, Pentium, I hope you all remember. I remember all this because I started my knowledge on IT, on computer system with 8-bit computers, 16-bit computers. Then we move into 386, 486. I don't think so. You all have ever heard about 386, huh? 386 computers, 486 computers, 586 computers. It goes into that series, Those days, Intel used to come out with that kind of series before they start promoting their CPU. Then later they move into Pentium. I hope you guys, some of you might remember Pentium. Then they come out with Pentium 2, and then the name changed into all kind of names that we have today, dual core, and so on. So this is how the history of CPU processor has gone through for many, many years. And this is the core business of Intel as well as AMD, those two companies that you guys have in Penang, as well as Itachi, Motorola, and so on. They all fighting among themselves or competitors in making chips. I'm not talking about RAM here or storage. I'm talking about processor. So the basic measurement, basic measurement for chip or CPU is MIPS, million instruction per second. So what we understand is the computer can execute millions of instruction in 1 second. Million. And the computers that we have today can execute even so much higher, uh, or what we call billions or trillions of instruction, because the processor is so powerful. It's already into gigahertz, isn't it? Gigahertz. Giga means it's already into billion and trillion. That is the speed of computers that we have today. So you need to understand that, that MIPS. So we have slow fetch execute cycle where the MIPS will be very low, such as keyboard, other simple character-based data transfer devices, such as your OCR, optical character recognition, one character at a time. OMR is even worse. Remember those days when we go for exam, we used to circle the answers, like SRP exam. Those days, if you guys still remember, A B C D, when the answer is A or B, you just circle A or B, or you mark it, right? And then we were told that it is not being marked by human being; it will be marked by machine. So what was the machine? The machine is actually OMR, isn't it? Optical mark recognition. So you'll pass through all your answer script through this OMR, and whenever there is a mark, the OMR will detect it and will mark as correct or wrong. That is optical mark character recognition, which is a very slow I/O. So we have slow I/O and we have super fast I/O that we have today. Like your phone is definitely super fast. Your smart TV, your laptop can upload and download millions of instruction or megabits, in a second. So you can always refer to those devices in order to do comparison for slower or higher speed. All right. So what you can see now is where you have a CPU with a register with the I/O register, with the bus as one unit. And this is an example of what we're going to discuss. CPU execute input, yeah, CPU execute input with the address 24, and is copied into the I/O address register, into the register in the CPU. In fact, there are a lot more detail. This is very high level. If you look into the detail, I hope there are more slides to explain this. How the register address is being copied from the input into the I/O. So that need to be explained in more detail, not as simple as this. Then how the I/O, either the keyboard, in this case over here is the keyboard, or mouse, understand whether the input or the data is output or input. Yeah, because keyboard, as you all know, is only input. Mouse also is input. But if the address is referring to screen, for example, then it is output. So which component will identify whether it is an input, whether it is a read or write, is the controller. So the message here is everything is being controlled by the controller. That's why it is known, the controller is known as a program I/O. We've programmed the I/O either to accept or to send, or in other words, we call to read or write. Read or write. Another continue, D, for example, let's say a character D coming in from the keyboard, you type D, a buffer in the I/O controller holds a keystroke D. And remember, I explained this in my previous discussion. The D will be converted according to the ASCII table. And in ASCII table, the D is referred to 68. Then the 68 will be converted into binary, because the rest of the component here doesn't understand D. They only understand 68 in binary, in 1 and 0. Yeah, that's how it works inside here. It doesn't work as a 68. If the component can understand 68, then it is wonders. But the component doesn't understand 68. The components only understand bits and bytes. So this D will be converted into bits, which is equivalent to 68, and then it will be transferred accordingly to the rest of the component. In this case, is being transmitted to accumulator to do some processing here. That's the whole idea. That's an example of how we program the I/O to accept input or output. Just an example. Then we have memory access controller, which connected to the memory. And as we all know, memory is transferring data between memory and devices. The devices can be I/O or CPU. And in your diploma level, I'm very sure you have covered registers such as what we call direct memory access, or MBR or MAR, memory address register, memory buffer register, and so on. Or we call it basically memory registers. So all those registers are important to transfer data between memory and other components of the system. DMA example, DMA, direct memory access. Let's take a look at some of the example. When you have a program that sorts a block of numbers, you have a program that you save onto the memory, main memory, that the function of the program is to sort a block of numbers. That is considered as one program. Yeah. And for the program to work, it has to link or access the memory. Please, like what I said earlier, this is a bit dry and a bit technical. If you need further explanation, please stop me. I can explain to you. Otherwise, you need to read through this slide line by line in order to understand. What I'm trying to explain to you is how a program inside this memory is being assessed to execute as a instruction in the CPU. Like in this case, a program that sorts a block of numbers. For example, you have three numbers, number 2, number 5, and number 7. How you sort these three numbers. I hope you still remember when you do programming. Let's say you have three numbers as an input, number 2, number 5, and number 7. And the question is asking you to sort these numbers from the largest number to the smaller number. How your program will work. Yeah, I'm very sure you as an IT student right now, quickly you can imagine how will be the code in your brain. So that's how the program is in the memory, and the program will be executed line by line. First, it will pick up one numbers, store the numbers in the register. Pick up the second numbers, compare with the first numbers. If the second number is greater than first number, right, you keep. If the second number is smaller than the first number, you swap. So those are the logic that you need to consider in your program. So in the same manner, your instruction, your memory, your CPU, and your registers will work. This is what we discussed when we discussed our assembly language example 2 weeks ago, 3 weeks ago, right? So I have explained this to you guys many times. Instruction will be fetched from memory into the CPU for execution. And CPU requires registers as a temporary memory to do the calculation. For example, 1 plus 1 is equivalent to 2. So you have to first pick up the first one, store it in a register, pick up the second one, you add to the first number, then your answer is 2. You display back the 2 into the display unit or into the RAM. So that requires a series of operation, operand and operators, like what we discussed a couple of weeks ago. So why I'm keep on telling all this is what we are covering in our syllabus for this subject. You need to understand all this in detail. How 2 plus 2 equal to 4 works. How 1 plus 1 equal to 2 works. So they might ask you a question, explain clearly how the fetch and execute cycle works in order to perform the simple operation as of below, 1 plus 1 equal to 2. So you must explain how 1 is being fetched from the memory, being loaded into the CPU, being stored in the register, and then what happened next, line by line. That is an example of direct memory access. All right, let me go back to my screen. I would like to check with all of you so that all of you are still with me, because I've been talking almost 1 hour with all of you and I need some feedback. So far, can all of you follow me? Do you have any questions or you need any further clarification?
No questions for them.
Okay, good.
Need to take a break.
Anyone else have any concern or question, need further clarification?
No further questions.
No questions so far, sir.
All right, okay, good. Okay, I know some of you joined late, doesn't matter. Miss Kelly from Penang, so far I received a request from Miss Kelly from Penang asking for my attendance. So I have submitted attendance to her as of last weekend. So actually, I'm taking your attendance from the blackboard. From the blackboard. Let me just share that quickly. I'm very sure all of you are very familiar where we take the attendance from the blackboard. It's over here. So I'm very sure all of you are very familiar with this. So help me to log in here. Remember, you see the October 5th, that means it's today's date. I'll pick up your attendance from here. Of course, some you have not, or maybe it's not refreshed yet. Don't worry. I also will check your meetings over here. That means you join the meetings over here. I have a lot of details that I can check. So that's how I mark the attendance. I cannot be calling one by one because there are almost 60 of you here. So it's a waste of time if I'm going to call one by one like a school children. So normally I will just check the details here. I will get everyone attendance from these details. So I make use of these details here. And please log in. Please log in into Blackboard if you have not. So it is very important to have access to Blackboard and to this MS Team. Okay, do you guys need a break or shall I continue?
A break.
Okay, if you need a break, let's take a 10 minutes break from now. It's 4:02. Let's come back around 4:10 or, plus minus 1-2 minutes. I'll talk to you shortly. Yeah, take a short break, 10 minutes break. Thank you.
10 minutes, right?
Yes, take a 8 to 10 minutes break. I'll talk to you around 4:10, 10 past 4 or 4:15, by latest 4:15.